Assalamualaikum and good day. Welcome back to my class on adaptive control and intelligent system. Today I would like to explain on pole assignment with regulator. Okay, let's have a look at this example. Okay, this is a plant with an output correlated with noise, and this is uncorrelated noise zeta. Okay, so the plant is having a transfer function of b over a polynomial x. All right, and it is actually having a disturbance, and it is a uncorrelated noise zeta with the polynomial of c over a. Okay, let's have a look at this problem and how we can actually design a controller with an objective is to remove the noise polynomial c in the output of this system. So having that objective, how can we do that? Okay, let's design a controller at the feedback of our system, okay, with a transfer function of g over f, okay, and that g over f is then multiplied with our input u, okay, and that polynomial g over f is as shown in this equation here. It is a polynomial with the model order nf and g, which is unknown. We're going to find it later on. Okay, so we design this controller. Okay, what happened is that when we have added a controller to our system, what happened is our closed loop system equation is now changing. So it's no longer as before. Before it was just z minus kb over a. Okay, but now your system closed loop system equation have added a controller, so it is already changing to what we have over here. Okay, so we're going to have our equation now. Yt is actually coming from this output is equals to your z minus kb multiplied by u, but u is already having this equation where f multiplied by u is equals to g multiplied by y. Okay, so then you're going to have this equation, closed loop system equation. All right, let's have a look at how these are being derived to get the closed loop system equation. So we have our y is now equivalent to the two input into the summing point, where you have the first one is u z minus k b over a. Okay, and the second one is from your noise, which is zeta c over a. That's your initial equation for y. At the same time, you know that your u is no longer just an input u is now becoming y multiplied by gf, okay, with a negative sign there. All right, so that is the equation for u. So we can add, or we can substitute u into the first equation here, okay, to eliminate the u function there. So I'm going to have y is equals to z minus k b over a multiplied by y g over f plus c zeta c over a. Okay, what I'm going to do is I'm going to multiply both sides with af. So I will have afy is equals to z minus k bgy, all right, plus zeta cf, okay, because the a has been cancelled out. All right, so that's what we have left, right? Then I will collect all the y together. So I have af plus, because there's a minus here of, I think I missed the minus. Remember, from u here there's a minus sign there, okay, from that u there. Okay, so we can oops, so there's a minus sign here. So instead of positive, this is supposed to be negative. So when I add that together, then it becomes positive. Z minus k bg, all right, that's your y, is equivalent to your cf with the zeta value there. Okay, so then you're going to get your y is equals to cf divided by af plus z minus k bg multiplied by your zeta. All right, so that is your equation. Okay, therefore for this particular problem, you can see that the closed loop system equation will give you a new characteristic equation, and that is at the bottom here. The denominator of your closed loop system equation is AF plus Z minus K BG. Okay, so this is your closed loop system equation, and that AF plus Z minus K BG is your new closed loop characteristic equation. Okay, why characteristic equation is so important? It will actually determine if your system is stable or not stable. Okay, so from closed loop system equation, we can obtain our poles. All right, so for pole assignment method, what we want to do is we going to assign a pole to the system so that the system remains stable. So if you look at your desired pole, so given by this equation T here, right? So the desired pole is something that you have to set by yourself. So we need, of course, when we want to design the desired pole, it must be a stable one, isn't it? So if you want to design a first order system, you need to design one pole, okay, one value of pole which is stable. The value must be less than 1. If you want to design a control with two pole, so your controller have to be, both of the pole must be having a value of less than 1. So this polynomial will be having a second order equation. Then if it's 3 pole and 4 poles, so your polynomial will actually follow the order of your what is the order of your controller that you want to design. Okay, so that is depend on your own application. So if you know that the application require you second order or third order, then you decide the value of pole accordingly. All right, so then we substitute that value of poles, the polynomial t, into this equation by multiplying with c. Okay, polynomial c is coming from your noise. You do not know the polynomial c, you need to do estimation. That is why I put a hat there. Okay, so that polynomial c is the estimated estimated polynomial from your error. So how to obtain this? You can use your least squared or recursive least squared and all, okay, and then do the parameter estimation to find the value of your noise from the polynomial c from noise from your system. It can be done by using whatever estimation parameter to identify that polynomial c. Okay, so I put this into a design rules. AF plus Z minus K BG must equivalent to the estimated C multiplied by the desired poles T that we have decided just now. Okay, and then if you look at this equation, these two equation from left hand side and right hand side, it must have a unique in order for you to have a unique solution, the model order have to be tally. Okay, so the model order for AF, in order for you to be able to multiply AF and add it with Z minus KBG, AF have to be the model order NA plus NF must be equivalent to the model order of NB plus NG plus K, because otherwise this equation cannot be added, isn't it? This equation cannot be added. So you need to do that, okay, to make sure that this equation can be added together. All right, so the model order NA, NF plus NF must be equivalent to NB plus NG plus K. All right, at the same time, okay, if we write this NF plus NG plus 1, so if I can rewrite this, it can become NF plus NG plus 1. It must be bigger, okay, then the model order on the other side of the equation, then the model order of NC plus NT. Okay, so we can decide the value of our poles if it's model order 2 or 3 or whatnot, okay, but then that will reflect the value the model order of our controller, because we need to design our controller, then the model order of our controller must be able to solve this in order for us to get a unique solution. Okay, so therefore from this first part, from this very important equation here, I got this formula where NF must not, okay, NF must be, NF must be equivalent to NB plus K minus 1, and at the same time NG must be equivalent to NA minus 1. So this is being derived from the first equation there. Okay, so this you must follow this, because we do not know what is the model order for NF for your controller F and controller G. You don't know the model order, so that model order must be decided based on the model order of your system. Otherwise, you're not going to get a unique solution. Okay, so I'll show you later on in example how to do this. All right, so now if you look at the system equation, the closed loop system equation, your yt, by replacing this value from the design rules, your yt will become f over t multiplied by zeta, your polynomial zeta. So you can see that your c has been eliminated completely, and the characteristic equation of your equation will now become only t, isn't it? Oops. The characteristic equation is becoming only t. So that t is something that you decided, and you can actually decide that it have to be a stable one. So you can see that your equation is now getting what you want, a stable poles, and stable poles with polynomial c has been cancelled out. All right. So from there, I can put this new closed loop system equation into my equation of ut. Then I will get that equation there. Ut is equals to g, negative g over f yt, and that ut is also equivalent to negative g over f zeta. All right. So this is what we have. Okay, you can see that the polynomial c has been cancelled out. Okay, but in order for you to do this, the inverse of that polynomial have to be stable. So we can do this by estimating it and check if it's stable or not. Okay, the non-invertible roots of c can be reflected into a unit circle to ensure that it is a stable polynomial. All right. In summary, if you look at your initial plant model, the model is actually ayt is equals to z minus k but plus c zeta. So it's having the polynomial c. This is the unwanted polynomial. You want to remove it, okay, so that your zeta here is remaining as a white noise. Okay, so you want to remove that polynomial c. So at the same time, you want your system to be stable, so you decide a set of stable pole decided by you, and that the set of desired pole is given by t just now. Okay, and the effect of polynomial c need to be removed. So this is the two objectives that you want to do. The first is to remove the polynomial c, and the second one is to ensure the stability of the system. You set the desired poles t. Okay, so with that, your design controller have to be shown. Just now we have derived it that your design controller is g over f. So if you put into the equation, it become f multiplied by ut, okay, is equals to g multiplied by your yt. Okay, so this is actually coming from the equation of your ut, u divided by y is equals to the transformation of negative g over f. So this is actually your controller just now, right? Okay, and then at the same time, you look at the characteristic equation. What happened is that you decided that the new characteristic equation of your system is equivalent to c over t. That c is actually estimated c, because you don't know the actual value of c, so you need to estimate it, and then you multiply with the desired poles that you decided on your polynomial t here. Okay, so this is the new set of the new characteristic equation of your system. You equate it with the characteristic equation of your system. Then from there, you can define the value of f and g. I'll show you in an example later on, so that this is easier for you to understand. Okay, so in order for you to design this algorithm, you want to actually put this into an algorithm. You can do that. Okay, we can actually put in a loop where initially you read the value of your output yt, okay, from the value of your output, and also of course the value of your input. You can initially assume that c is equals to 1, because you don't know the polynomial c in the beginning, isn't it? So you can assume it equals to 1 in the beginning, and then you estimate your plant model of your plant by using least squared, recursive least squared. Find out what is the value of your polynomial a, polynomial b, and any delay that you have in your system. You can update that from your least squared. At the same time, you can do that with your polynomial c as well. So these are all estimated parameters. So you know that your system is keep changing in its parameter. So every time it change in parameter, you do the estimation. Okay, so once you have done the estimation, you put in the same loop your design controller according to this formula here. Okay, so your design controller will be put there, and you will update the value of your controller F and G based on the updated value of your parameter plan A, B, and also the polynomial of noise C. Okay, and then you're going to generate the new control output U with the formula that we have we have derived earlier. Okay, so then you update this, and then you know that your system is keep changing in parameter. That's why you need to design this kind of adaptive control. So what you do is you put this in a loop so that every time the parameter of your system changes, okay, you can detect this with least squared, and within that least squared loop, you're going to put the new formula for your controller, which is the value of G and F. Okay, and that value of G and F is estimated using this design rule, so that your system is always stable and the polynomial C in your noise is always being cancelled out. Okay, so I will show you in an example how to utilize this design controller, into a real. Alright, let's have a look on an example on how to use your pole assignment regulator. Let's have a look at this system. Let's say this system is described by the following equation, where we have your polynomial A, okay, multiplied by your input by your output Y, equivalent to polynomial B, which is also having some delay, you can see that, okay, multiplied by your input U, plus polynomial C multiplied by your noise, so that making this noise not completely white noise. So what you want to do is you want to design a controller with a pole assignment regulator, so that the system have a closed loop pole at a single pole at Z equals to 0.7. So you are designing a closed loop pole, one single closed loop pole to the system, to ensure that the system is always stable. Okay, so from this equation, we know already that this is your A, so that's what I have here. Your A is equivalent to this. Okay, so from there you can straight away know that the model order of this is up to Z minus 2. Therefore, the model order for A is NA equals to 2. Okay, then next one you have is your B with that polynomial there. Okay, that is actually Z minus K multiplied by your polynomial B. Okay, so we can actually split that okay, to have two model order. So Z minus K multiplied by polynomial B is, if I factorize the Z minus K from this equation, okay, I can factorize it by Z minus 1. Alright, so what remain in that equation will be your B, your polynomial B. So Z minus 1 is your delay. Okay, so you know that your delay is having the model order of 1. Alright, and your polynomial B is going to be 1 minus 0.5 Z minus 1. So that is your polynomial B. Okay, so initially it's coming from this polynomial here, but it is actually having two things there, Z minus K and polynomial B. So I just actually factorize it to get the value of Z minus K, factorize and split from the polynomial B. Okay, so that's what we have, and then we know that model order B from that equation, model order B is 1. Okay, and then lastly you have a look at the polynomial C that you have here. Okay, so how do we get this polynomial C? Maybe perhaps from parameter estimation. Okay, and it is equivalent to that polynomial. So we can just say that, right, your polynomial C is this value here. Then the model order is, because the highest order is Z minus 1. So the model order is for NC is 1. Okay, so you have all this value. That it is very important, because using those model order, you're going to then find out what is the model order suitable for your controller F and G. Okay, so, and don't forget, it is also asked in the question is that you need to design the system with poles of Z equals to 0.7. Okay, how do we put that into the zero or the whole equation? So we know that the pole have to be 0.7. Okay, so that is coming from equation of your characteristic equation must be from z minus 0.7 equals to 0, isn't it? Okay, so if I multiply this equation top with 1 over z, okay, I just want to multiply with 1 over z to make it in terms of 0 or the whole, because 1 over z is actually z minus 1. Okay, so if I multiply that with 1 over z, over here this is going to give me 1, over here is going to give me 0.7 divided by z, but divide by z is the same as having z minus 1 there, okay, equals to 0. Why? Because it's multiply with 1 over z. Okay, so that is the polynomial of my t in time in polynomial form. Okay, so that's a t in polynomial form in a 0 order whole. Okay, so then with that I know that the model order is minus z minus 1, so the model order is t is equals to 1. All right, so having this model order, we can then put into our controller. So if you recall the controller from the previous slide, the controller is that f multiplied by ut is equals to negative g yt. All right, so and also your design rules, there are one design rules is that your characteristic equation af plus z minus k bg must equivalent to ct. C is to cancel the polynomial c, and t is actually to make sure your system is within the stable poles. Okay, you decide the stable poles just now to be 0.7. Okay, so to ensure that the system have a unique solution, I have already shown in the previous slide that these are the requirement. Okay, and from there I have actually simplified that nf have to be this value here. Okay, and f is equals to nb plus k minus 1, and g is equals to na minus 1. So I'm just going to put the value for my model order. Okay, so nf will be determined by that equation, and ng will be determined by that equation. So I put the value of nb just now from the previous slide. Nb is equals to 1, k is equals to 1 minus 1, so nf straight away I found it equal to 1. So for my controller, the parameter, the polynomial of f have to be with model order 1 only. So then we can straight away write, okay, because of that requirement, my nf can only be equals to 1 plus f1 z minus 1. So I need to then find out what is f1. Okay, that is the design for my design equation. Okay, but the model order I already decided based on this equation here. Similarly, I will do that for my g. Okay, I'll put the equation of g is ng is equals to na plus minus 1. Okay, na plus 1, na minus 1 here. So na is 2, so we put 2 value there, minus 1, then I get my ng is equals to 1. So similarly for my polynomial g, the model order, the highest model order that I can create for my g is 1. So then my model order, my polynomial g will be defined as this equation here. It is equals to g naught, because it is at the denominator, so we can put that it is at the numerator, so we can put that as g naught plus g1 z minus 1. Okay, so we just put g naught there just in case it will give you value. So if it doesn't give you value, then it's just going to be g1 z minus 1. Okay, so g naught we just put it there so that to check if it's going to give you any value at all. Alright, so this is g at polynomial, the polynomial g with model order 1. Okay, then we put all these equation, this controller, okay, your f and your controller g into your design rules equation, which is this af plus z minus k bg equals to ct. So I'll put all the polynomial into this equation. This is my polynomial a, this is my polynomial f, this is my z minus k, this is my polynomial b, and this is my polynomial g. Okay, and it is equivalent to polynomial c multiplied by polynomial t. So put this into this equation, and we need to expand those equation. Okay, it's a bit tricky, so you have to do it properly, and I have expanded it. All right, so you have to expand all of them, so we get this very long equation here for your AF plus Z minus KBG equals to CT. So these are the polynomial that we have, a long polynomial that we have for our when we expand this equation, the design rules. All right. So what we're going to do then, we're going to compare the coefficients. So by first expand the equation and then compare the coefficient on the left hand side and the right hand side. And then from comparing the coefficient, we get into this equation for Z minus 1. Okay, so you have a look at on your left hand side what the value that you have for Z minus 1. Okay, so you have Z minus 1 is equals to minus 1.2, Z minus 1 plus F1. Okay, and also you have Z minus 1 plus your G naught here. Okay, and then on the right hand side for Z minus 1, you only have a negative 0.11. Okay, so similarly you're going to do for your Z minus 2. So for your Z minus 2, you have over here is a 0.85. Okay, Z minus 2. Okay, and then you have minus 1.2 Fz minus 2. Okay, so you just put that one minus 1.2 F1. Okay, and then you have for your here is another Z minus 2, which is negative 0.5 G naught, and then I have another one is plus G1 Z minus 2. So I'm going to put all that into this equation. So and compared to the right hand side, I have only 0.28 Z minus 2. Okay, so I put that into that equation. So that is by comparing coefficient of Z minus 2. Then I'm going to do again similarly with Z minus 3. So Z minus 3 will have, I will have that 0.85 F1 plus minus rather 0.5 G1. Okay, Z minus 3. And then on the right hand side of my equation, I will not have any Z minus 3, so that is going to give me a 0 value. So that is my equation. Okay, so I have three unknowns, I have three equations. So when I solve these, I can use calculator, and I can put all these value, and then I can solve this equation. Then I got my solution is F1 is equals to 0.58 and G naught is equals to 0.62, and then G1 is equals to negative 0.884. Okay, so these are the value that I got by solving these three equations with three unknowns. Okay, by doing substitution and whatnot, or you can just use your calculator to do it. Okay, you get this value. Therefore, you can then put back this value into your polynomial of controller. Okay, so you have for your F1 is equivalent to this polynomial here, and G naught G1 G is equals to G naught plus G1 Z minus 1, and it becoming this polynomial here. So these are the new value of your controller. Then you're going to put this controller into your closed loop feedback system just now. Okay, according to the design rules that we have in the beginning of the system that I derived just now. Okay, so it's there. So that's your G and your F. You're going to put that into your equation. So having to have this kind of derivation, what happens is that first, your system will be stable with the set of poles that you have decided earlier. Number two, your polynomial C at this equation will be cancelled out. Okay, so that is for this particular problem. All right, in summary, so that's all for the problem. Okay, so in summary, pole assignment regulator, what you need to do is you want to remove the noise from your output. You can do that by shifting the open loop poles into a desired closed loop poles that you decide by yourself. Okay, number three, the noise polynomial can be cancelled out only if you can actually make sure that the system polynomial C is a inverse of it is a stable. and to make sure it is stable, we can move it to an invertible roots of C into a unit cycle to ensure stability of polynomial C. Okay, so that will be all for your pole assignment regulator. I will give you more past year questions so that you can go through and check the past year questions and check the solution as well, so to make sure that you understand this pole assignment with regulator. Okay, thank you very much for your attention.